Hello, everyone. Uh, Thank you for joining. My name is Vecchio, and we have two talks about Parquet plugin today. I'm going to talk about the Parquet plugin and its usage, go into some background about the Parquet format, and then I'll pass it over to Ilhan Gelle, and she'll talk about her HPCC summer internship, and the project that she worked on. So first, a little bit about me. Like I said, my name is Jack Del Vecchio. I started at LexisNexis as a HPCC Systems intern, developing the MongoDB plugin. From there, I was hired on part-time while I was finishing my studies, working on the Parquet plugin. And then once I graduated, I was hired on full-time. And since then, I've been working on various areas of platform improvement, working on maintaining the plugins and stuff like that. So th this talk will be focused on Parquet. What is Parquet? How can it help you? And why you should care about it. So some of the topics. First, we're going to talk about the advantages of Parquet, Parquet files compared to logical files, and the necessary information you might need to keep in mind when you're working with Parquet files. And then we're going to go into a short introduction into arrow partitioning and kind of put it in context with logical file parts and HPCC systems. And then I have a couple short demos that I'll have at the end of the slides, and we'll just go through some code um, and step through it. So first, I want to remind everyone that before we get into the presentation, please, if you have questions, don't hesitate to put them in the Q&A. Myself and Ilhan will be available to answer any questions. So first, some advantages of Parquet, um, why you should care about it, essentially. One of the big things that Parquet has going for it is its interoperability, how easily it integrates with third-party tools. Here's just a couple big ones like Hadoop and Spark, Google BigQuery and Pandas for Python support. The ability for us to open another gateway for data to flow into HPCC is huge, allowing us to interact with these environments much more seamlessly. In just a single line of code, you can output a Parquet file and then have that available for use with other third-party tools. It's something that if you're looking to expand and integrate other tools, Parquet can certainly help you with that. So some of the advantages of Parquet come from the file read performance. And because it's a column-based structure, it allows for some different advantages than you would get through CSV or XML type files. So one of these advantages is that you can read columns selectively. So um, this is kind of a breakdown of the structure that you would see in a Parquet file. So you can see one of um, the column metadata inside the footer. That's going to store things like the min-max of the column, information like that. So that allows you to push filters down to the read level. So say, for example, you have a large file that you want to read, but you only care about a certain value. You can skip over entire chunks of data if you know that that value is not within the min and max of that column. Um, and then from there, you can also specify specific columns to read. So if you have, a large data set that's a really wide data set with, 50 fields or whatever it may be, and you only need to uh, compare against, two fields, um, Parquet can save you that read time by not having to read through all that data. It can just choose the columns and then return that to you. So that's kind of one of the nice things about Parquet. It makes reading large files very easy, um, and it gives you a lot of things uh, that you can work with. And then I'm just going to go over quickly some of the compression types that Parquet offers. Um, with there's compression with the platform and Thor files and flat files and that, but this gives you some additional algorithms that you can use to compressed Parquet files. Um, and one thing I want to mention is that for all the Parquet files, or for, excuse me, for all the compression types that Parquet supports, when you are reading a Parquet file, the plugin will automatically um, uh, detect the type of compression that was used. So when you're reading files, it's not something that you need to take into consideration necessarily. Um, but when you're writing, it gives you some options. Um, so for example, Snappy is a compression library developed by Google. It aims for quick compression rather than total size. So it's going to be one of the faster compression methods, but with a trade-off of performance. Um, so gzip is a very performant compression algorithm, very common, very high levels of compression. Brotli uses multiple compression algorithms together to provide a state-of-the-art compression similar to all the other types. Um, and similarly with C standard, um, it's a compression algorithm that has high levels of compression. Um, they are similar in most ways, but they have some trade-offs, and it's nice that Parquet has gives you the option. So hopefully the Parquet advantages are a little more clear, and why you'd want to use them. So now I'm going to talk a little bit about how they differ from files in the HPCC systems ecosystem. So how do they compare to logical files? So the first thing to note is that Parquet is implemented as a plugin. So it right off the bat isn't going to get a lot of the advantages that you would get with logical files. For example, when you define a record in ECL and you want to read a file, it does not have access to that ECL record definition. At the moment, the plugin just reads the entire file, reads all the um, reads all the fields that it can, and then passes them to the platform, and the platform matches it up to the ECL record. So at the moment, that's one of the things that we're interested in is closing that gap between Parquet files and logical files. So another example is logical file information metadata isn't stored in DALI for Parquet files. Um, so if you're working with a Parquet file in your ECL code, and you have, a data set defined on it, um, that that file isn't going to be tracked, or information isn't going to be published anywhere. It's just going to be a Parquet file on your machine. Um, and similarly, um, HPCC systems cluster nodes can't access files on different nodes. So the Parquet plugin can only read files local to it. So uh, wherever that cluster is running, that's where it's going to read the file from that node. If you have multiple workers, each worker will be capable of reading its own file, but it'll only be files local um, to that node. So unlike native file formats that require you to first import the file to the cluster, you can just read Parquet directly. Um, so if you take a look here, it's it's specifying a path to a Parquet file, and then using the parquet.io.read function to read that data set. This is just an external file in the drop zone um, that is being read directly. In the case of native file formats, you have to put it in the drop zone, then import it, and then use the logical file name to specify um, to reference it. So you can skip a step. It makes it easier to uh, it makes it easier to um, work with the Parquet files. It's quicker, but you do have that trade-off where you lose some of that information, and that's because uh, it's skipping an entire spray step. Um, so when you import a file, it's splitting it up and spraying it to all the nodes on the cluster. Um, when you're reading a Parquet file, you're just reading that Parquet file directly. There's no intermediary step where it's setting it up on the cluster and spreading it out for the nodes. Um, so there is some drawbacks, but you can skip that step. And I really want to make a point that when you are referencing Parquet files, these are files local to the machine that the cluster is running on. So for example, when you have a logical file, they'll show up in the logical file page in ECL Watch. Um, and in ECL Watch, there's all kinds of information there. There's tracking through XREF. Um, you can track files, delete files, um, all that are, known to the cluster, delete files that are not known to the cluster. There's a row viewer that you can peek inside the file with. Um, all of these great tools that are available for logical files sprayed to the cluster are not there for Parquet files. Um, so I want to make that clear that um, this is something that uh, is in progress, adding a new format for files to be read so that Parquet gets all this information, gets all these advantages. Um, that's something that is we are working on. So another thing that is different with ECL files and Parquet with ECL records and Parquet files is the record definitions. So that the types that are in the record definitions are mapped to Parquet types. Um, so if you look at the table on the right, um, most of the types match up fairly well. Boolean goes to Boolean, integer to int. If you define the number of bits in an ECL type, it'll select the subsequent Parquet type. So example, if you um, define an integer 3, that'll give you a 32-bit integer in the Parquet side. So just going down the list, real 4 goes to float, real 8 goes to double. Um, if you are using ECL to output a Parquet file and then taking that Parquet file to a third-party tool, it may be necessary to know the schema in Parquet types as opposed to what the ECL record definition is. So some of that is nice to keep in mind when you are outputting Parquet files. Um, and a pretty big difference between Parquet files and ECL is the naming conventions of the field types. So in ECL, everything is case insensitive. Field names are all lowercase. But in Parquet, you can have uppercase letters in the field names. So that creates an issue if you're trying to define a record in ECL for a Parquet schema that has fields with uppercase letters because you won't be able to define that. So for this, it has XPath support, so you can define special cases of records like that. So I think we're ready to take a look at some code now. Um, if you take a look up here, um, we are defining the file name of an external file, the file name of a logical file that we're going to write to. Um, and here we're working with a CSV file, and we're going to uh, create a spray action. So what this means is we're going to take a file that's in the drop zone, an external file, and we're going to spray that to the cluster. And what that means is if we're working on a Thor cluster and you have n Thor workers, it's going to create n file parts and split up the data so that each Thor worker has a file part to read. So this is what the spray step is doing. And you can see here how you have to configure all the options um, just to set up the uh, action. And then it defines a record for the CSV file, and then uses that record definition to define a data set. This the file at the destination isn't there yet because we haven't sprayed it. So it is going to spray it and then output the data set. Um, so this is a lot of lines. This is a lot of lines of code to do basically two things that you can do with the Parquet plugin in a single line of code. Um, so what's happening here is it's reading an external file, which is what this output is doing, reading from the data set, and then this is writing it to a different. This is writing the data that we read in to a new file location, which is what this spray step is doing. And you can see here just how much simpler the Parquet plugin makes reading a file, an external file. Um, and it's uh, the interface for the ECL library is much simpler than having to mess with all of this. So now I'm going to go into arrow partitioning, and I'll explain the context in context of HPCC logical file parts. So as I've said earlier, when you import a file to the cluster, um, it will, depending on how many workers you have, if you have, for example, a 50-way Thor, it would create 50 file parts and divide them up so that each Thor worker has its own file part. And the way that it divides it up is it divides it by rows. Um, and this is conceptually different from how Parquet partitions files because Parquet is a column-oriented storage format. So it is going to divide the files up by columns. And so what that looks like is, for example, if we are doing high partitioning, and high partitioning is it basically just means that the field names that you are partitioning on um, are uh, are available in the file name, the directory names. Um, so if you partition a data set with these fields, you will have a directory structure similar to this with a top level directory where all the partition files are written, a directory for each value. So year equals 2021, year equals 2022, and so on. And then by month. And then so all of the rows that have year 2021, month equal to 1, will have orders count and revenue stored in it. Um, and it just stores the two fields that are not that weren't used for partitioning. So inside the Parquet file, if you were to look at it, you would only see two fields, or two columns, excuse me. It actually figures out what the other fields are based on the directory structure. Um, and so the other partitioning, for the other type of partitioning, very similar, is directory partitioning. And you can see here, the only difference is that the field names are not available in the directory name. So when you are reading a high partitioning, excuse me, when you're reading a directory partitioned data set, you need to specify what those fields are that they were partitioned on. It's just a single extra step, but that is the main difference between them. Um, and so hopefully this makes it, a little clearer all that is going on with Parquet and how it can help you and some of the differences between logical files and HPCC native file formats. Um, so now I'm gonna go over into a short demo, talk about some of the code that I have, and yeah, we'll go from there. Okay, so now we're going to take a look at some short ECL code. Um, First, we're going to start off with importing a Parquet data set. So we're going to take a look. So the first thing that you need to do when you are working with the Parquet plugin is import the library. So this has the read and write functions for all of the normal files, directory partitioning, high partitioning. It gives you the read and write functions for each of those, making it nice and easy. And then here, I've just exported a module with the layout. So this is the New York taxi data set, very common data set for open source development. Um, you can see here all the fields, and we have a couple that do have uppercase letters, and I've defined the XPath for them. Um, without these um, without these XPath tags, the plugin wouldn't be able to match the fields to these defined in the record. So from here, you can see it's just as easy, just a simple single line. We are going to read from this location. This is an open directory on my computer, meaning I have permission to read from it. But it can be anywhere that you have permission from, or the drop zone in your cluster. Um, just reading from the Parquet file and exporting that definition. So if I go over to the runnable file, I'm just going to output the result of that. And I can run that here and then show you the output. So here's all the fields. And so, like I said, that's about as easy as it gets. From there, you can treat it like any ECL data set that you would. You can do joins, any kind of thing that you would want to do. So with that, 2 lines and this file, it's very easy. So for the next example, we're just going to take a look at some ECL code that is reading a CSV file. So this is the same data, just in CSV format. You can see I'm using the same record structure. In 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 this case, the XPath isn't needed, but it's just going to be extra information. Um, that's how it's going to be output when we see the results. So it's similar. I had to do some extra work where I had to spray the CSV file to the cluster, and then I can use the data set on it. So from there, I have the definition. So we can just output this, um, and you can see the data is there, just the same. Um, there is a difference between the date times because of how Parquet stores dates as milliseconds after the epoch. Um, but that's due to the implicit compression that Parquet offers. It has very good codecs for some of the types that it has. So here, um, if you're working on HTHOR or Thor, you can distribute the file. We don't really need to do that. Um, so oops, if you're just looking to change the file format, that's pretty easy. So we can take the file that was defined in CSV dataset.ecl and use that dataset to write to a Parquet file. And like I said, the first step is import Parquet, and then we can do um, Parquet io.read. My Copilot is trying to help me a little too much. It's okay. Um, and then we can use the layout that we defined in that file. Um, and excuse me, we want to write. Write layout and then the location that we want to write to. And we can just write to the drop zone. Sure. And actually, Copilot doesn't really know the syntax. So now if I compile that, it will work. And then if I run that, it should still output the CSV dataset file. . it wants to be a little slow, so we'll move on to the next line while we wait. So now that we've written that Parquet file out, we can go ahead and read it back in. Um, and then once we have read that file back in, we will have a dataset definition pointing to that Parquet file. So anytime we need to reference that, it'll be pulling from the data from the Parquet file, and we'll get that improved read speed um, that we want. So actually, this needs to be the layout, and then the data set that we wrote to. So if I compile that, there's no issues, and then I can run it. Um, I'm not sure why they're not running, but if I look at some, oh, it failed. Okay, so I tested this demo to make sure it would work. So there is already a file there. So we have to define the overwrite option. Set that to true. Um, if we overwrite the file, it'll delete it and write a new one. Um, so now if we run it, it should succeed. We give it a second. Be patient. Hmm. Well, this one succeeded. So you can see that this was when I tried to write it the first time. Um, okay, there's result one. And this normally takes like 2 seconds, but now I'm doing a live demo, it's taking forever. So that's okay. We can just move on to the next one. Um, it's a little bit more interesting anyways. So here's the intro to arrow partitioning. We're going to partition this data set. Um, um, and we're basically just using the same definition that I used for the first example. So I have this module for the Parquet data set that I'm exporting the output of the read function. Um, if we go over to oh, we can see it succeeded. So I'll just show you these results real quick. Um, that was saying. So, and the reason that the timestamps aren't different now is because I wrote it as a string. So you can specify what you're defining the types as um, when you are using Parquet. Um, so we'll go to the last example real quick. Um, just using the same definition. Um, we are using the hyperdiction method, writing the dataset that we have a Parquet file for, um, defining true because we want to overwrite any existing files, and then this is the syntax for selecting the fields to partition on. So the vendor ID will be the top level directory. Vendor ID equals 1 or vendor ID equals 2. You can see the values for vendor ID. And then the second field that we're going to partition on is the pickup location ID. Um, I picked um, two fields that didn't have too many unique values since it will create a directory for each value. So if you can see there's 249 unique IDs at least, there's going to be at least 240 directories in the high partitioning. Um, so we go ahead and run this. This will take a little bit because it's going to um, read through the Parquet file. split it into chunks, and then split those chunks up again based on the partitioning field. Um, so I can show you um, what the output of that looks like. So if I just go to um, that directory that we're writing to, you can see the two top level directories, vendor ID 1, vendor ID 2, and then we go down one level and you have all the pickup location IDs. So it takes some knowledge of the data that you're partitioning. It takes some understanding of what the data type is, but it can be very powerful because it can be used to selectively read some of these fields, and that can drastically reduce the amount of time that that read operation takes. Um, so it is expensive on the right side, um, but we can see here the data um, is all there. So you can see again, I'm reading from the original Parquet file that has the timestamps in milliseconds. Um, but that is pretty much it. Um, hopefully that made hopefully that made sense. That was useful. Again, if you have any questions, feel free to drop them in the chat. I'd be happy to answer them. So I'm going to go ahead and pass it over to Ilhan Gelle. She's going to talk about her fantastic project and her presentation.
Hello, everyone, and thank you, Jack, for the introduction. I'll be presenting my talk on the test suite for the Parquet plugin, and my name is Ilhan Gelle. So to tell you all a little bit about me, my name is Ilhan Gelle, and I was an intern this past summer here at HPC Systems. I worked mainly on the test suite for the Parquet plugin, and Jack was my mentor. I'm based in Dallas, Texas, and I'm a junior at the University of Texas at Arlington studying computer science. This talk will focus on how the test suite for the Parquet plugin was developed, as well as how it works. So now to talk a little bit about today's objectives. We're going to start off with some background on the project, the big why behind the project, and why I was working on it. Then we're going to go into testing methodology, why certain things were chosen to be tested and why certain things weren't, as well as the test suite specifics, how many test cases there are, and how the test workflow is, as well as the results. And then we're going to end off with a video demo, which will show you all how it works and how to run the code. So now some background on the project. We're going to talk a little bit about what the test suite is and how it works. It's a series of automated tests that's leveraging the regression suite. So it's a subclass of the regression suite test cases, and it tests the Parquet plugin's functionality and performance as well as operations. The big why behind the project was to ensure accurate data handling, as well as to detect issues early and validate the performance of the plugin. And the big benefits behind this test suite is that there's going to be increased reliability, faster development as things were tested accurately and quickly. Then there's going to be as well as improved data integrity and consistent quality when developers are using the plugin. So now let's talk a little bit about the project's goals. So the first goal was to create a comprehensive test suite that tested the Parquet plugin's operations, functionality, compression types, as well as error testing and testing corrupt files, testing schema, as well as the partition testing. The next thing was to bring attention to the Parquet plugin as it's slightly underused in the platform. So kind of just to promote broader adoption of Parquet for efficient and high performance data storage and processing. The last one was to create clear and accurate test suite documentation because the plugin does not have a good amount of documentation. So when I was working on it, I had to outsource a little bit. And yeah, so the test suite documentation aims to help people start from the beginning and understand where to find the test cases, how to use them, and a lot of documentation is useful. So now to talk a little bit about some background on the test suite. It covers 42 ECL and Arrow data types. We include some compression testing, so we evaluated Arrow's compression algorithms like Snappy, gzip, and Brotli and LZ4. And then this was to test the performance whenever it came to compression and how Parquet works with compression. And there was some operation testing, which was the Parquet IO.read and Parquet IO.write functions, as well as the spraying and despraying speeds, and the handling of empty or corrupt files, as well as schema reconciliation. So each of these tests compares the output against key files to determine success, with ECL Watch being used for monitoring these results. And then this image kind of just shows you how Parquet uses columnar instead of row group formatting. So now to talk a little bit about the test suite specifics in terms of development. So the test suite was developed using Python, ECL, Parquet files, the regression suites framework, and C++. So for Python, I mainly use Kaggle to collect data sets, but whenever I needed edge case Parquet files, I needed to kind of create my own. So that's how I use Python to generate specified Parquet files, especially with data types whenever I wanted more than one data type in a file. Yeah. And then for ECL, all of the data types are in ECL code, and the plugin is imported using ECL code. And then Parquet files, every file has a Parquet file that's either being written to or reading out or compressed or partitioned. So every test includes a Parquet file or more than one. And the regression suite framework, as you'll see in the demo, includes the framework for how to run all the test cases at one time or run them individually. And then C++, the original Parquet plugin code was made in C++. So whenever I found any issues in the plugin, I went in C++ code and corrected it there. Okay. And now to talk a little bit about our demo, I'm going to start off with some images showing you how the test suite was set up, and then we're going to move on to running the entire test suite. So this upload.ecl file will show you that all the files that are in the class Parquet are run whenever you run the test suite. And then this file specifically has no key file because it just shows us how the test suite needs to be run. And you see that it's being cleaned up here as well. And then it also includes a sample Parquet file. So it kind of just shows how the test suite should be run and a starting point for all the files to start at. This XML file is an example of all of the key files being compared against whenever the test suite is ran. And then these are the Parquet files that are included in our download directory that is a starting point for the reading test cases where the files can be read from. All right, now to start off with the demo. Okay, so now the test cases are running, and as you can see, it says 15 queries because of the compression types. You're going to see uncompressed, snappy, gzip, Brotli, LZ4, and then DSTD. So the way that the test suite is ran, first you can see the ECL test query, which is just the framework for all these tests being run. And then in this example, I'm targeting the cluster Thor, but you can HTHOR, but you can choose Thor or Roxy as well. And then, as I mentioned before, the run class Parquet at the top of all the files puts all these files into a group so that they can be run consecutively. And then in here, I'm just running all the files that have the extension .ecl and our Parquet files, but you can run them one by one. So example, this Parquet compressed.ecl file, you could change this portion to Parquet compressed.ecl and just run these test cases instead of all of them. And then now we're running the corrupt file, and this one intentionally fails because we are trying to read in a corrupt file. And the main point for this one was we wanted to make sure that there was correct errors popping up whenever we fed an error into the code. And then I also tested an empty Parquet file, which we wanted to just see if that would give us an error. And then in this overwrite option, it'll be included in the results as well. But the override option will show you that you cannot, in the Parquet IO.write functionality, you need to specify true, or if you leave it empty, if you run the code again, it will give you an error saying that this test is already there. And then we tested schema, and then you can see size. And then a big point about this is the test cases only take about 50 seconds per run. So it's pretty quick as well. And then Now to move on to some results. First off, we have the spray and despraying tests. So this testing started off with a 15.59 gigabyte CSV file and was compressed down to a 5.25 Parquet file, a 6.75 JSON file, and a 10.8 gigabyte XML file. So to compare these results, we can see that Parquet only took 20 seconds to spray and 24 seconds to despray. And then JSON took 28 seconds to spray and 33 seconds to despray. XML took 59 seconds to spray and 114 seconds to despray. And then CSV took 56 seconds to spray and 70 seconds to despray. So as you can see, Parquet was the fastest for spraying and despraying, and made the file about 33.7% of the original CSV file. So it was the best whenever it came to compression and spraying and despraying speeds. So this is an example to show you how you can go from a record structure like this and then read in the file and get it to be like this in your ECL watch. So in this example, you can see that I'm using the ECL structure for mapping of the data types. So this one is an integer ID. You can see string, decimal, 8, and Boolean. And then in this, well, you can see in this example, this is how you would use parquet.io.read. You'd have the record here as the first parameter, and then the file path as the second parameter. And then in this example, you see at the bottom how that would look like. And then in the overwrite test, which intentionally fails, you'll see that in this example, I did not include an override option to true. This test will pass the first time, but the second time, whenever you run it again, the file is already there. So it'll tell you an error telling that the file already exists, and to delete it, set the file to overwrite. So the second time that you run it, or the third time, you don't run into the same problem. Now to talk a little bit about documentation. The README provides step-by-step instructions for running the tests, understanding the test cases, and interpreting those results. The directory includes all 10 of the ECL test files, expected output XML files for validation, and sample Parquet files that were used for testing purposes. To conclude, the project demonstrates the Parquet plugin's superiority and efficiency, storage optimization, and performance compared to others that are used in the platform. Mentioned before, JSON, XML, and CSV. The tests confirmed its ability to handle complex data types and compress large data sets effectively, which is useful to us. These findings should encourage wider adoption of the Parquet format in the HPC systems community. Thank you so much for listening. I've listed my contact, and thank you.